Well, good morning, everyone, and welcome to the 28th Summer School. Just echoing what is already said before, I'm extremely grateful to the Institute for hosting us and hope that our collaboration will continue for many years more. And I'm especially grateful to Elchanan and Stephen for organizing this particular summer school. As Elchanan said, one of the important ingredients of the summer school is your participation. There'll be lots of lectures in the next 10 days. I'm afraid you'll have a very heavy dose of me today, but there would be no point to meeting here unless you participated too. We could just video ourselves and show the videos. By the way, the lectures will be videoed, and if you miss anything, you can see it on the replay, and the lecture slides will also be posted online. But it's indispensable that you should be asking questions, making comments, pointing out errors. That's your job. So I have a rather ambitious task before me today. I would like to present essentially all the major results in mechanism design up to the early 1980s to set the scene for the meat of the summer school, which is to come. So I've allocated myself 4 hours today, and I hope that we all survive. And I'm going to go very quickly because I'm hoping that at least some of this material will be familiar to a good many of you. But if you're not following what I'm saying, do tell me, and I will stop. And we have a microphone here. Since things are being recorded, it would be good if comments and questions were recorded through the microphone. Okay, mechanism design. You probably all have an idea of what mechanism design is about. I like to think of it as the engineering part of economics. A lot of the time, maybe most of the time, economists look at a particular existing institution, a market, say, and try to explain or predict what outcomes that institution will generate. In mechanism design, we do exactly the opposite. That is, we start with the outcomes that we would like to have. These are our goals, and then we ask, well, are there institutions or mechanisms or games that we could create which would result in these desirable outcomes? And if that's the case, if the answer is yes, then we want to know what form these institutions might take. There are many, many applications. If we're a community and we're deciding whether we're going to build a bridge to connect us to the next community, a public project like that might be decided according to a mechanism. If we're allocating goods to buyers through an auction or some other institution, that's a mechanism. If we're trying to regulate carbon dioxide emissions, the Kyoto Protocol or the Paris Accords, that's a mechanism. On a more micro level, a contract between a buyer and a seller saying who is responsible in the future for delivering the good and paying for the good and when it's going to occur, that's a mechanism. Even at a fundamental political level, the constitution of a country, which determines how laws are passed and when elections are held, is also a mechanism. So the applications are truly very general in scope. And now let me go to the formalities. If this were a classroom course, I might spend half hour or so on the informalities, but since we have so much material to get through, I'm going to jump right to the basic model, unless there are questions at this level. Okay. So we'll have a set of people, a set of individuals, numbered 1 through n, and we'll have a set of outcomes, possible outcomes, which can be interpreted differently according to the application. So if we were talking about public projects, set A would consist of all of the public projects that we could undertake, including no problem. If we're talking about private good allocation, the different possible allocations of goods across buyers would be the outcomes. If we're in a political context and we have an office which must be filled by one of several candidates, the list of candidates will be our set of possible outcomes, and so on. We'll have a set of possible states of the world. A state of the world basically determines all of the data that are relevant to the decision to be made. So in particular, the state of the world theta will determine each individual's preferences over outcomes. So the standard notation that I'll be using, let me make sure that I push the right button for the, yes. The standard notation will be UI of A and theta is individual I's payoff from outcome A in state of the world theta. Theta also will determine the production technologies, perhaps individuals' endowments, anything that is relevant for outcomes. Now, for today, I'm going to not worry about technologies and endowments. I'm just going to be worried about preferences. So, although in principle, the set A should depend on theta, I'm going to ignore that connection for these 2 lectures. Now, for now, and actually throughout this first lecture, but not this afternoon, I'm going to assume that players know their own preferences. So they may not know the state of the world entirely, but they at least know their own utility functions. That's true of a lot of mechanism design, but not all of it. And we will get to the, I hope there'll be time to get to the point this afternoon where we drop this assumption. Sorry?
UI constant forever? Each agent has the same UI forever?
Well, so the question is, does each agent have the same UI forever? We'll suppose that this is an atemporal model at its foundation. It's a static model, but we could interpret it as a dynamic model where A, the choice, is a dynamic choice. And in that case, theta could involve changing preferences over time. So although I will analyze the model statically, it's in principle extremely general. Okay. Now, how do we model? Yes, question. Maybe I should pass the microphone around.
Do the players know the preferences of the other players as well?
At the moment, we're not saying anything about that. That's going to depend. That's going to depend on the equilibrium concept. So at the moment, we're not making any assumptions, but we will talk about that later. How do we model society's goals? The typical way is via what's called a social choice rule or a social choice correspondence. This is in general, it's a set-valued function of the state of the world. So f of state theta is going to be a subset of possible outcomes. You can think of f of theta as being the desirable outcomes or the optimal outcomes or the best outcomes in state theta. These are the outcomes that we would like to have. And just to give a couple of examples of social choice rules, if all we cared about was Pareto optimality, we could look at the Pareto, or the efficient social choice rule, which picks out all of the outcomes which are not Pareto dominated. If we were in a private market context, we might look at those allocations which could result from competitive equilibria. Those would be the competitive equilibrium allocations. If we were in a political context where we were voting, we might look at the set of outcomes which would beat all of the other outcomes by a majority vote, the set of majority winners. If we were Benthamite utilitarians, we might look at the set of outcomes which maximized the sum of people's utilities. And I'm sure all of you can think of many other potential social choice rules, but these are just a few examples. Now here is the thing that makes mechanism design interesting. If the mechanism designer or the social planner or the government or whoever is in charge knew the state of the world theta, mechanism design would be very easy. We could just, if this is the government could say, well, I know that theta is the state, so I'm going to impose an optimal outcome for that state by law or decree or whatever. But the thing that makes the subject interesting is that the planner or the government doesn't know theta. And so that means that we have to proceed indirectly through a mechanism. What is a mechanism? It's simply a game form from strategy spaces to outcomes. So G is sometimes called a game form or an outcome function. It differs from a standard game in game theory because it doesn't specify the payoffs. It specifies the physical outcome. We would have to know the state of the world to to know what the payoffs are. And the whole point is that the planner who is choosing G doesn't know what theta is. So we look instead at a game form where capital SI is player I's or individual I's strategy space, and the result of everyone picking a strategy is some feasible outcome. The planner knows. The planner might, yes, the planner will know the set of possible utility functions, but not which one actually holds.
Only uncertainty if the planner is theta.
Yeah, we've modeled things so that all uncertainty is captured by theta. Whatever uncertainty there is, we can put that into theta. That's right. So when this game form, this mechanism is played, we'll suppose that there's an equilibrium outcome. There might be multiple equilibria. So let E sub G of theta be the set of possible equilibrium outcomes of the mechanism G in state theta. Of course, this set is going to depend on the equilibrium concept, and we're going to talk about several different equilibrium concepts today. But whatever that equilibrium concept is, we'll say that that G implements F, the social choice rule F, if the set of equilibrium outcomes coincides with the set of possible optimal outcomes for any state theta. What I've just described is what's sometimes called full implementation. That is, we want every optimal outcome, every outcome in f of theta, to correspond to some equilibrium of G. We might be satisfied with a weaker concept where some of the optimal outcomes can occur in equilibrium, maybe not all of them. This is called weak implementation. It turns out to be easier to characterize implementation when we demand equality, and so largely for that reason, that's been the concentration of the literature. But if we have characterization of full implementation, we get weak implementation for free because weak implementation just means full implementation of some subcorrespondence of F. So we don't have to do any extra work for weak implementation. Now, how do we interpret this mechanism G? Again, that depends on the circumstances. We could think of G as being imposed by the government. So G could involve a tax and spending policy, for example. We could think of it as arising automatically or endogenously. So markets themselves are mechanisms. They're not really chosen by anyone, but they're there, and we can analyze them in the same way that we analyze artificial mechanisms. We can think, as I was suggesting earlier, of G as being chosen a priori as the constitution for society. So in advance of a country actually existing, the founding fathers and mothers can choose a constitution which will determine how the country is run politically. That's a mechanism as well. Or on a more humble level, a relationship between a buyer and a seller, a bilateral contract, can be thought of as a mechanism as well. Now, I said that there's a variety of solution concepts in mechanism design, and basically every solution concept that game theorists have come up with has been applied in one form or another to the mechanism design literature. Let's start with the solution concept which demands the least of players, and that's dominant strategy equilibrium. As most of you probably know, we say we have a dominant strategy equilibrium of a mechanism G in state theta if, regardless of the strategies that the other players use, and S minus I you should think of as the vector of strategies that players other than I are using. So if, regardless of the strategies that the other players are using, player I is at least as well off using his dominant strategy Si prime as any other strategy Si prime. And when I say that this concept is very undemanding of players, I mean that player I doesn't have to worry about what other players are going to do. Player I doesn't have to even know what other players' preferences are, because player I can just play his own dominant strategy, regardless of those other preferences. Now, I've just told you what the strength of dominant strategy equilibrium is. The downside, as we'll soon see, and as you probably already know, is that unless we make some restrictive assumptions about the set of possible preferences, we're not going to get very far with dominant strategies. Let me let me go back to the previous slide. Any questions at this point? Is everyone with me? Turns out that to analyze dominant strategy equilibrium or dominant strategy implementation, it simplifies matters if we assume that players are never indifferent between two different outcomes. So we're going to assume that if A and B are different outcomes, players always have strict preferences. This makes things much tidier. But we're going to drop this assumption later on when we move to other solution concepts. One nice feature of this no indifference assumption is that we can very easily conclude that if F is implementable in dominant strategies, there can only be a single possible optimal outcome in any state. In other words, F has to be single valued. And here's the argument. Suppose that there were two optimal outcomes in state theta, A and B. That would mean that there has to be a dominant strategy equilibrium leading to A, and there has to be a dominant strategy equilibrium leading to B. Now, what happens if we look at this configuration of strategies? That is, player 1 is using the dominant strategy for B, and the others are using the dominant strategy for A. Well, if the outcome of the mechanism is not A, then we have a problem. Because if individual 1 prefers A to this outcome, then he would never use S1B. He would be better off using S1A, getting A, rather than this outcome. But that contradicts the assumption that S1B is a dominant strategy. And we have exactly the opposite problem if the inequality goes the other way. So that tells us that the outcome for this configuration of strategies has to be A. But now let's change the other players' strategies from SI A to SIB one at a time, in iterated fashion. Each time we make that change, we have to get A. Otherwise, we run into this kind of contradiction. And ultimately, we conclude that G of S1B up to SNB must be A. But that contradicts the assumption that we started with. And so that means that there's always a unique equilibrium outcome in any states. This is a good time for me to mention the revelation principle. The revelation principle, a very simple idea, means that when we're looking for mechanisms to implement a social choice rule in dominant strategies, we can look at a very simple kind of mechanism in which players are basically just announcing their utility functions. And in equilibrium, players will have the incentive to announce their true utility functions. In fact, announcing your true utility function will be a dominant strategy in any states. And a mechanism in which you announce your preferences and in equilibrium you announce your true preferences is called a direct revelation mechanism. And from this point on in our discussion of dominant strategies, I'm going to assume direct revelation mechanisms. And the proof of the revelation principle is extremely simple. If we had some other mechanism, G, which implemented F, we could simply define G star of a n-tuple of utility functions as being the outcome that would arise if players use the dominant strategies for those utility functions in the implementing game G. And so by construction, we now have a direct revelation mechanism constructed from G. Okay, so now I said we don't get very far. We don't get very far with dominant strategies when we make no restrictions on preferences, the formal statement of that result is the Gibbard-Satterthwaite theorem. And here is that statement. Suppose, first of all, that there are at least 3 possible outcomes. I'll say in a moment what happens if there are just 2. So there are at least 3 possible outcomes. There is an unrestricted domain of preferences, and what that means is that for any n-tuple of utility functions, there exists some states in which people actually have those utility functions. So no restrictions on preferences. The social choice rule is Pareto optimal. That is, if in a given state, theta, everybody prefers A to B, then B cannot be the outcome. By the way, we don't actually need Pareto optimality for Gibbard-Satterthwaite. There's another assumption, the assumption that F is onto A, which could be used instead, but this is certainly a convenient assumption to make, so I'm going to impose it. And of course, if F is implementable in dominant strategy equilibrium, then F must be dictatorial. That's the negative consequence of these 4 assumptions. The idea that there will be some player I who basically always gets his way. If A is optimal in state theta, then it must be the case that the dictator, I, prefers A to any other outcome, B. And since, I'll take your question in a second, and since in a democratic or reasonably egalitarian society, we don't like the idea that there's a single individual who is determining all the outcomes, we tend to view this as a negative result. Yes, and please use the mic. Okay.
And do we assume the no indifference assumption as well here, or no?
Yes, I'm
So
imposing
under
the no indifference assumption. That's right. Otherwise, individual I might actually be indifferent between A and B. Right. Right. Yes.
So it seems the unrestricted domain assumption is allowing the set of potential. So there's a lot of thetas, essentially. It's at least Rn, it looks like, roughly. Is there any traction to be gained by putting more structure on that leads to any of a less pessimistic result in an interestingly general setting?
Well, we're going to come to a reasonably general setting in the afternoon, the setting of quasi-linear preferences, which have been intensely studied. But at this level of generality, the answer is all right. Let me put it this way. Suppose there were 3 alternatives. So A consists of 3 alternatives. In that case, there are 6 possible strict orderings. The Gibbard-Satterthwaite theorem says if all 6 strict orderings are possible, then you get a dictator. But it turns out that if you can eliminate even one of those strict orderings, then you get possibility results rather than impossibility results. And yes, there is a literature on what sorts of omissions of preferences lead to what sorts of implementable social choice rules at this general level. Yeah.
Is the requirement of Pareto optimality really as you wrote it? Because it's usually a weaker requirement. Pareto optimality means that only one player is sharply better and the others may be equal, no?
Well, there's no indifference here. Remember, we're ruling out indifference by assumption. Okay, so that's the statement of the theorem, and since this is a foundational class, I'll give you a proof. There are lots of proofs of this theorem. Many of them make use of the arrow impossibility theorem, but I want to show you a proof which works from scratch without any prior knowledge. So let me sketch that proof. I forgot. I wanted to say what happens if there are only two alternatives. If there are only two alternatives, then we can decide things by majority. If there's just A and B, we can choose A if a majority prefers A to B, and B if a majority prefers B to A. That works perfectly well for two alternatives, not as well for more than two. So the proof I want to give, I'm going to give for the case of two individuals. It's not hard to extend this argument to more than two, but it would take more time than I want to devote to this theorem. So I'll leave it to you to do the extending. And I will post references where you can read all these things in detail. Okay, so let's look at a particular pair, because there are only two people, of utility functions. I'll call this a profile of utility functions, U1 star, U2 star. Suppose it's the case that person 1 ranks A first and person 2 ranks B first. If they both have the same top alternative, that alternative would have to be the outcome because we're assuming Pareto optimality. So suppose that they're different. A is not B. And let's suppose that the optimal outcome for this profile is Z. And the first thing I want to show is that Z has to be either A or B. It can't be some third alternative. Now, why is that? Well, suppose it were some third alternative. So Z is not A or B. And let's look at this slightly different profile where 1 puts A at the top, 2 puts B at the top, and A is second. And we know that there is such a profile because we're assuming unrestricted domain. Now, what are the possible outcomes under F for this profile? Well, the outcome can't be B, because if it were B, individual 2 in this profile would pretend to have utility function U2 double star, because here he gets Z, which is below B, and here he gets B. So that would violate the fact that it's a dominant strategy. We're looking at a direct revelation mechanism. That would violate the assumption that it's a dominant strategy to tell the truth. So we can't get B. We can't get Z, the outcome up here, because Z is Pareto dominated by A. Both players prefer A to Z. So that the only remaining possibility is that A is the outcome for this profile. Now, if we reverse the roles of the two players and we look at the symmetric profile with the roles reversed, that tells us that for this profile we must get B. But now we're going to run into trouble, because suppose that we look at the profile U1 double star, U2 double star, where 1 ranks A first, then B, and then the rest of the alternatives. 2 ranks B first, then A, the rest of the alternatives. We can't get outcome A for this profile, because if we did, 2 here would be better off pretending to have utility function U2 star, because 2 prefers B to A. If the outcome here is A, 2 is better off with the outcome here, which is B. So we can't get outcome A. We can't get outcome B because otherwise individual 1 would misrepresent. And we can't get any other outcome because A and B Pareto dominate any other outcome. So there's no possible outcome that can correspond to this profile. And that means that our assumption up here that we got outcome Z different from A or B must have been false. So in other words, we've proved this claim that we either get A or we get B for such a profile. And there are basically 3 steps to the proof of Gibbard-Satterthwaite. This is the first step. The other 2 are equally simple, but if you didn't follow this, you won't follow the others. So make sure that you understand this. Any questions about it? All right. Well, for this argument, for the argument I just showed you, we know we get A or B. Let's suppose that we get A. There's a corresponding argument we could make if we got B, but the 2 cases are clearly symmetric. What I now want to show is that for any other profile where person 1 ranks A first and person 2 ranks B first, we get the same outcome A. Now we've already shown that for this other profile, we have to get either A or B. That was the first claim. So let's suppose, contrary to what I just said, that we get B rather than A. Now let's look at this mixed profile where person 1 has utility function u1 star and person 2 has u2 b. What is the outcome here? Well, it has to be b. If it were a, which is the only other possibility, then person 1 here with utility function u1a would pretend to have utility function u1 star. Here he gets b. For this profile he gets b. Here he gets a, which he prefers. So we can't have b as the outcome. That means that for any profile where 1 ranks a first and 2 ranks b first, the outcome must be a. And now the only remaining thing to do is to look at profiles where perhaps A and B are not top ranked. That some other alternatives, X and Y. Now we've shown that if it's A and B that are top ranked, person 1 has his way always. To finish the proof, we have to show that person 1 has his way in a profile like this, where it's X and Y that are up at the top. If we show that person 1 has his way here as well, then person 1 really is a dictator. Now for this profile, we know from the previous argument that we either have to have X or Y. Suppose it's Y, so 1 doesn't have his way. And now let's look at this profile here, where 1 ranks X first and then A, 2 ranks B first and then Y. Well, first of all, let's note that we can't get B here. If we did get B here, 1 would be better off pretending that he has utility function u1a, because then he would have his way and get A. So we can't have B here. And that means that we have to have X, because X and B are the 2 top-ranked alternatives. Has to be one of them. So if it's not B, it's going to be X. But now we see that person 2 is better off pretending to have utility function u2, because then he gets Y. He prefers Y to X. X is down here someplace. So he wants to manipulate. So we've reached another contradiction, and that means that we can't have outcome Y here. It has to be X. And that completes the proof, because now we've shown that in all possible circumstances, 1 gets his way. Whatever he top ranks will be the outcome of the mechanism. 1 is a dictator. So that's the Gibbard-Satterthwaite theorem. And as I said, you can pretty straightforwardly extend this to any number of players beyond 2. Question. Please use the mic.
What happens to the theorem if we don't restrict ourselves to dominant strategy implementation?
Well, that's actually what we're going to turn to next. Because we run into a negative result here, the literature has gone in two directions. One is to weaken the equilibrium concept, and we're about to look at Nash equilibrium. Another direction, which we'll concentrate on this afternoon, is to restrict the preferences. And so it turns out that if we have quasi-linear preferences, we can use dominant strategy implementation, at least to some extent. And we'll see that this afternoon. If you could pass the mic along.
So what happens if you assume that there are infinitely many possible outcomes?
That's fine.
That's fine?
This argument doesn't rely on a finite number of outcomes at all. Yeah,
You
there
may
can-
not have. I guess it's not straightforward what it means to be dictatorial then, because you might not have a favorite outcome at all.
Well, we're assuming
Yeah.
no indifference. So even if there was an infinity of outcomes, oh, I see what you mean. Yeah, so you're right. In that case, there has to be some regularity condition.
Right, but I guess
a
if
closed set of outcomes and continuous preferences.
if
something
all
like that.
preferences have to have a favorite,
Yeah,
then
no, that's right. That's right. There are some technical issues which have to be addressed if there's an infinity of outcomes. You're quite right.
I was wondering where you used that there are at least 3 outcomes, because if there are only 2, then dictator seems coincides with majority rule. Is that the conclusion?
That's exactly right. Of course, you can't really see that with just 2 people, but if there were more, if there were more than 2 people, that's exactly right.
I mean, in this case, couldn't you implement something that you say we do A whenever both people are for A, but when one person is for A and one person is for B, we do B, and then then you wouldn't have a dictator, right? Because sometimes you choose B, even though agent 1 doesn't like B. Shouldn't it? No, agent 2 doesn't. I mean, both could be the ones who prefer B, right? And therefore you wouldn't have a dictatorship if you only have 2 alternatives.
That's right. Yeah.
You need the 3 alternatives for the Gibbard solver.
Any other questions about Gibbard Satterthwaite? Okay, so as I suggested, this result tells us that we can't get very far with dominant strategies, at least with very general preferences, and so the next natural step, I would say, we might take is to be less demanding in our equilibrium concept and move from dominant strategy equilibrium to Nash equilibrium. Now, we're weakening the equilibrium concept, but of course we're now demanding more of players, because now it will be the case that players will have to forecast what other players are going to do in order to figure out what they do themselves. So just as I characterized what was implementable in dominant strategies, dictatorships with dominant strategies, I want to characterize what is implementable in Nash equilibrium. And it turns out that the key to Nash implementation is a condition called monotonicity. So what does monotonicity mean? suppose that in some state theta, outcome A is optimal. And suppose that we now change the states, we change the preferences in such a way that outcome A does not fall in anybody's preferences vis-a-vis any other outcome B. So in other words, if A was above B in the original state theta, it remains above B in the new state theta prime. Then monotonicity says that A should be optimal with respect to the state theta prime. Because it hasn't fallen in anybody's preference ordering relative to any other outcome. Oh, and I should say that although we were ruling out indifference in the Gibbard-Satterthwaite argument, we're not going to rule out indifference anymore. So these lines just repeat what I said about this formal definition. It will turn out that monotonicity is a necessary and almost sufficient condition for implementation in Nash equilibrium. Now, the fact that it's necessary means that we have to live with it. I mean, whether you like it or not, if you want to implement F, you have to satisfy it. Now, it turns out that a lot of the social choice rules that I mentioned earlier on in the introduction are monotonic. So, for example, the set of Pareto optimal outcomes is monotonic. So if A is Pareto optimal in state theta, that means that for any other outcome B, there is somebody who thinks A is at least as good as B. Otherwise, B would Pareto dominate A. But in going from theta to theta prime, that same person who has this preference must have this preference, must think A is at least as good as B in state theta prime as well. But that means that B does not Pareto dominate A in state theta prime, which means that A is still Pareto optimal in theta prime. So the set of Pareto optima is monotonic. And by similar argument, you can show that the set of competitive equilibrium allocations is monotonic. You change preferences so that an equilibrium allocation doesn't fall in a person's preference ordering, then that allocation must still be a competitive equilibrium at the same prices as before. Same thing with majority rule. Majority rule is monotonic. I won't go through the argument now. You can follow it on the slides later. Now, utilitarianism, where we sum utilities, fails to be monotonic. And you could have anticipated this, because monotonicity, by its very definition, is an ordinal concept. It only depends on rankings, not on cardinality. It doesn't depend on utility numbers at all. Utilitarianism does depend on utility numbers. And so you can see right away that there's a conflict. And here's an example. Suppose that there are two people and two possible outcomes A and B. And here's a table of utilities in state theta. So for outcome A, person 1 gets utility 3, person 2 gets utility 1, and similarly for outcome B, if you add up the utilities of A, 3 plus 1, you get 4, which is bigger than 1 plus 2. So in state theta, A is the utilitarian optimum. But in state theta prime, where we've changed, well, we've actually only changed one of the payoffs. We've changed this payoff from 2 to 4. Now, B is the utilitarian optimum because 1 plus 4 is bigger than 3 plus 1. But notice that we haven't changed the way that either 1 or 2 ranks A and B. In this state, person 1 ranks A above B, 2 ranks B above A. Same thing down here. So the ordinal rankings haven't changed. So that shows that utilitarianism violates monotonicity. So here's the critical lemma. If F is implementable in Nash equilibrium, it has to be monotonic. And here's why. Suppose that social choice rule F is implemented by G, and let's suppose that in state theta, A is an optimal outcome according to F. Well then, by definition of implementability, there has to be a Nash equilibrium of G in state theta, which leads to outcome A. That means that for each player I, if I deviates to some other strategy SI prime, I can't do better than playing SI, the strategies which lead to this Nash equilibrium outcome A. Right? All right, so now let's look at another state, theta prime, which satisfies the hypothesis of monotonicity. That is, A, in going from theta to theta prime, A doesn't fall in anybody's preference ordering. If A was above B before, A is still above B. What we have to show is that A is actually optimal in state theta prime. Now, why is A optimal? It's optimal because this same Nash equilibrium in state theta is also a Nash equilibrium in state theta prime. How come? Well, suppose that this inequality were violated. Suppose that in state theta prime, person I was better off deviating to SI prime. Well, then from star, he would have been better off deviating from SI to SI prime in the original states. Right? So that means that this inequality has to hold. We are assuming that S1 through Sn was a Nash equilibrium in the original state, so deviations can't pay here, so they can't pay here either. So this is a Nash equilibrium in state theta prime, but since it's a Nash equilibrium, the outcome has to be optimal. That, again, by definition of implementability. And that tells us that A must be optimal in state theta prime. And that proves the lemma. Any questions about that? Now, what about the converse? If F is monotonic, is it implementable? Actually, the answer is no. That is, we can construct monotonic social choice rules that are not implementable, but it turns out that they're pretty weird. Any such social choice rule has to have some pretty odd features. I'm not going to give you an example today, but trust me, they're peculiar. And it turns out that if we impose an additional assumption, which in many settings is actually extremely weak, it's called no veto power, then that combined with monotonicity guarantees implementability if there are 3 or more people. Mechanism design is interesting in economics because usually going from the case of 2 people to 3 people makes things harder. There are lots of things that are true about 2-person economies that are not true of 3-person economies. But in mechanism design, it's often the case that the n equals 2 case is harder than n greater than 2, and for a good reason. The trick in mechanism design, in constructing mechanisms, is to make sure that people are punished appropriately when they deviate from equilibrium. But how do you identify a deviator? If there are only 2 people, knowing who the deviator is tricky. If you see something that's out of equilibrium, it might have been that 1 deviated and 2 was doing the right thing, or that 2 deviated and 1 was doing the right thing. It might be difficult to know which was which, to know who to punish. But if there are 3 or more people, then it's much more easy to identify the odd man out. And that intuitively is why implementation with 3 or more people tends to be easier than with 2. And that's certainly true for Nash implementation. But we need this additional assumption of no veto power. Now, what does no veto power say? It says that if everybody in society agrees that outcome A is the best. In other words, if everybody agrees that A is at least as good as any other outcome B, except possibly for one person, perhaps person I thinks otherwise, then I does not have the ability to veto A as an optimal outcome. That's no veto power. And the reason that I say that it's very weak is that there are, or at least in many settings it's very weak, is imagine that there are 3 or more players, and imagine that an outcome, whatever else it involves allocating some private good across players. Well, under the usual assumptions that we make about preferences, each person is going to want all of the private good for himself. So to find an outcome A which satisfies this condition, so that A is top ranked for all but one person, is impossible, because if I think A is top ranked, that means I'm getting all the private good and you're not. And so no two people can agree that A is top ranked. And so in those circumstances, no veto power is satisfied automatically because the hypothesis can't be satisfied. So, but even in circumstances where we're not allocating private goods, there are lots of social choice rules that satisfy no veto power. If we pick out the Pareto optima, that clearly is going to satisfy no veto power. Majority rule satisfies no veto power. And for the reasons I just went into, if we look at the competitive equilibrium social choice rule, that's going to satisfy no veto power as well, as long as there are at least 3 people. So now we come to the positive result, contrasting with Gibbard and Satterthwaite. If a social choice rule is monotonic and satisfies no veto power, and if we have at least 3 people, then it's implementable in Nash equilibrium. And I'm going to take you through the proof of this, which is constructive. That is, we will actually create a mechanism given F, which implements F. But before I do that, let me just pause and make sure everyone is with me. Any questions or comments? Yeah, let me pass the mic back.
So we're still assuming that all agents know their own preferences, but not necessarily the state itself?
No, well, in this case, they are going to have to know the state in order to be able to predict what other people are going to do.
Okay.
So actually, that's weaker than knowing the state, but somehow they're going to have to predict what strategies the other players are going to use. They have to know enough about the states to be able to predict the other players' strategies.
Okay.
Right. So it's more demanding of players than dominant strategy equilibria. This afternoon, I'm going to look at the case where players don't necessarily know what strategies other players are going to use, but have beliefs about the distribution of those of possible strategies. That's the case of Bayesian equilibrium, but that I will talk about in the afternoon. Any other questions about the statement of this result? Okay, so we're going to construct a mechanism, And the first thing to decide on is what the strategy space is. So what we're going to have each player do is make an announcement. Player I will make an announcement about the state, theta I. So here, actually, in this construction, I'm assuming that players actually do know the state. If they didn't know the state, but they only knew people's preferences, they would be making a statement about the preferences. Knowing the state is stronger than necessary, but let's assume that they know the state. So I is going to make an announcement about the state, not necessarily a truthful statement, but a statement. I is also going to propose an outcome, AI, and then for tie-breaking purposes, and this will be used only when we need a tiebreaker, player I is also going to announce a positive number, MI. Question. Where is the mic there? Oh. No. Theta I is I's announcement about theta. It's an announcement about theta. That's right. So there are three steps to the construction, three cases that we'll look at. We'll first look at the case where everybody is announcing the same state. So theta 1 equals theta 2 equals theta n equals theta. Again, it's not necessarily the true state because the mechanism designer has no idea what the true state is, but all the players are announcing state theta, and they're all announcing the same outcome. A1 equals A2 equals AN equals A. And furthermore, the outcome that they're announcing happens to be optimal in the state that they're announcing. So suppose that these conditions are satisfied. Then it's very natural to assign as the outcome to these strategies outcome A. So that's what we'll do. That's case 1, or case A. Case B is exactly the same as case A, except that there is one player, player I, who is deviating. So everybody else is announcing the same state, theta, and the same outcome A, and A is optimal for that outcome. But person I is announcing some other states. Some other outcome, AI. And here, by the way, is one of the places where we use the fact that there are at least 3 people. Otherwise, we couldn't tell that I is the odd man out. So what is the outcome in this case? Well, it all depends on what outcome I is proposing. If I is proposing an outcome AI, which is no better than A, according to the state that the other people are announcing, state theta, then I can get outcome AI. It's fine. if you're different, if you're proposing something different, as long as what you're proposing is not better than what the other people are proposing, according to the preferences that they are ascribing to you, which are preferences ui of state theta. But if you're greedy, if you try to get something that's better than A, then you don't get it. You get outcome A instead. So that's case B. Any questions about that? And case C is just a catch-all covering every other possibility. In every other possibility, we use a tie-breaking rule. So the outcome in case C is we look at whoever is announcing the highest integer, the highest number, and we let that person get his favorite outcome, AI. Now, there could be a tie there, in which case we can break the tie. We can have an additional tiebreaker and, for example, choose the person who has the lowest index and is announcing the highest number. Okay, so microphone.
So given this C case here, it seems this would yield some existence problems, or are ties zero probability?
So ties will never occur in equilibrium. Okay. So one advantage of mechanism design over ordinary game theory is that we get to construct the game. So we can always construct the game so that technical problems like existence are solved by construction. And in particular, they are solved in this construction. I think I saw another question someplace. Yeah. Do you want the mic? Okay. You want me to explain case C? B. Okay. So B is the case where everybody but player I is playing strategy theta A. So they're all announcing the same state theta. They're all announcing the same outcome A. And person I is doing something else. He's announcing theta I, AI, and he gets AI if, according to the other people's announcement, AI is not better for him than A, the outcome that they're announcing. But if he announces an AI for which his utility, given their announcement, is higher than A, then the outcome is A. So he's not allowed to be too greedy, as I was putting it before. If he's too greedy, the other people have their way.
Maybe what is missing is that in the first case, AI must be in FA, in F theta. AI, in the first subcase there. No, here, and in B?
Yes.
Then the first, in the big brackets, the upper part.
Well, AI doesn't have to be in here.
In this case, if this happens then?
No, AI doesn't have to be optimal.
In the subcase of this, you see, you are choosing AI there.
Here.
Yes.
Yes.
But
This is I's out. This is the outcome that I is announcing.
Yeah, but you want to implement an optimal thing, right?
Yes, so if we get outcome AI, it's not going to be optimal. That's right. But that's okay. It's not going to happen in equilibrium. So I haven't shown that any of these conditions lead to good equilibria. I'm just giving you the construction. And now I will show that this construction actually works. But I haven't done that yet.
Is it important that the sign or the equality is in the first part of the bracket? Here, that there is the equality in the upper part? I'm asking whether it's important or whether it could be also maybe the other way.
Yes. This is, if indifference is possible, it is important that this be a weak inequality here, if that's what you're asking. Yes. Yeah. It's not that. This is not just a matter of taste. You want this to be a weak inequality, and you want this to be a strict inequality. That does matter. Okay, so I've shown you the complete construction, and now all that remains to do is to convince you that this construction actually implements F. And to do that, there are two parts. First, we have to show that in state theta, for every optimal outcome A, there is a Nash equilibrium in state theta that gives us outcome A. That's that's the contents of this claim here. And then the second part is to show that in state theta, every Nash equilibrium is optimal. And for that, we'll actually need a few claims. But let's start with claim 1. So if A is optimal, there exists a Nash equilibrium for the mechanism we've constructed that leads to outcome A. And that's pretty easy, because suppose that everybody is playing the same strategy. They're announcing state theta, the true states. They're proposing outcome A, this outcome here, and they're announcing, well, actually, it doesn't really matter whether they're announcing the same integer or not, because the integer is not going to come into play here. But let's suppose that they're all playing integer 1. Then I claim that this is a Nash equilibrium in state theta, and that we get outcome A. Well, this is going to make use of parts A and B of the construction. So if everybody is announcing the same state and the same outcome, and the outcome is optimal for the state that's being announced, then by construction we get A. So getting part 2 is easy. Now, why is this a Nash equilibrium? Why is this announcement a Nash equilibrium? Well, person I could deviate and play some other strategy, and in fact, by construction, person I can get any outcome AI which is no better than A for the true state. So he can get anything which is on or below his indifference curve through A. But none of those outcomes is actually better than A, and so he doesn't gain by any such deviation. And so, as claimed, S1 through Sn is a Nash equilibrium in state theta, and it leads to outcome A. So every optimal outcome in state theta can be achieved by a Nash equilibrium. Any questions about that? Okay, so all that we have to do now is show that every Nash equilibrium leads to an optimal outcome, that there are no non-optimal equilibria. Now, there are two ways that we could get, well, actually, there are three ways we could get non-optimal equilibria potentially. We could have everybody announcing the same thing, but announcing a false state. We could have everybody but one person announcing the same thing. And we could have everything else. So we have to consider those three cases in turn. So the first case is what happens if everybody is announcing the same state and everybody is announcing the same outcome, and the outcome that they're announcing is optimal for that state, but the state is actually not the true state. The true state is theta prime. Well, suppose that these announcements are a Nash equilibrium for the true state, theta prime. Then we better make sure that the outcome that results from these announcements is optimal. Otherwise, the mechanism doesn't implement F. So this is where we're going to use the fact that we know that F is monotonic. This is actually the only place where we need monotonicity. So how do we prove this claim? Well, we know, first of all, that when players play these strategies, the outcome is A, because we're back in case A again. And so suppose that in state theta, this inequality holds for some player I and some other outcome B. In other words, for the announced state, A is at least as good as B for individual for individual I. Now, by construction, if player I deviates and plays theta B1, he can get outcome B, because by construction, he can get any outcome he deviates to, provided that it's no better than A, according to the state that everyone else is announcing. So player I can deviate and get B. But that means, since we're assuming that S1 through Sn is a Nash equilibrium, that B cannot be better than A for the true preferences. Because if it were better for I under the true preferences, I could deviate and get B. The fact that he doesn't, the fact that this is a Nash equilibrium, means that this inequality is false. And so if A is at least as good as B under the false preferences theta, A must be at least as good as B under the true preferences theta prime. And now you see where monotonicity comes in. This implication, this implies this is true for every player I and every state theta prime, and therefore, by monotonicity, we know that since by assumption A was optimal with respect to the false preferences theta, A must be optimal with respect to the true preferences theta prime, and we've proved the claim. Any questions about that? By the way, I should, if you're getting anxious at this point, this is by far this proof is by far the most complicated of any that I'm going to show you today. Everything in the afternoon is about 1 page long. So this afternoon will be simple compared to the two big proofs this morning. All right, so that's the case where everybody, where we get a Nash equilibrium, where everybody is announcing the same false states. What happens if we have a Nash equilibrium where everybody but I is playing theta A, but I is doing something else? So there's an odd man out. And here, again, it's important that there be at least 3 players. Well, suppose that this is a Nash equilibrium. We want to make sure that all Nash equilibria are optimal. So suppose that this is a Nash equilibrium. We have to show that the outcome is optimal with respect to the true preferences, the true states, theta prime. Why is that? Well, notice that everybody, except possibly for player I, can deviate from this configuration in such a way that case C of our construction applies. Remember, case C was the catch-all case where A and B didn't apply. And in case C, basically, it's whoever chooses the biggest number wins. So everybody, except possibly person I, can deviate from this configuration and get his favorite alternative by announcing that alternative and announcing a high enough integer. So the fact that this is a Nash equilibrium means that none of these players J gain by deviating and getting their favorite alternative. That means that they must be getting their favorite alternative already in Nash equilibrium. That means that everybody but player I is getting his favorite alternative. No veto power then says, well, if n minus 1 players are getting their favorite alternative, that alternative must be optimal for the true state theta prime. And that covers this case where there's one man out, one odd man out.
But if player J would like to get AI,
If player J would like to get AI, then he wouldn't necessarily be the odd man out. Because there would be two people stating.
But he could announce some other state, right? Right. He doesn't have to announce the same.
Okay, so we need.
Well, but actually, even if he did announce the same state, we'd still be in case C, because case C applies whenever there's more than one man out as well.
Yes, if there are at least three.
If there are at least 3 players, then we're okay. Right.
Can I ask another question?
Sure.
Is the complete information assumption that they all know the state, is that a simplifying assumption for the proof, or is it needed for the theorem itself?
It's needed. Well, it's needed for the idea of Nash equilibrium. If you're going to predict what strategies other players are going to play, you don't have to know the state, but you have to know enough to be able to predict their strategies. So knowing the state is more than you need to know in order to predict other players' behavior. But whatever it takes to predict other players' behavior, that's what you need to do a construction like this.
But here you actually need to.
Well, in this yes, we could generalize this construction so that it applied whenever players could predict other players' strategies. The same ideas would work. So in that sense, this is more specific than necessary. But, you have to know quite a lot to apply Nash equilibrium. So it is very demanding, much more demanding than dominant strategies. And that's why it's important to look at the intermediate case of Bayesian equilibrium, as we will this afternoon. Okay, so one more claim, one more case to consider. What happens if we have a Nash equilibrium where we don't have unanimity and we don't have one man out? That is, we have a case C Nash equilibrium. Well then, everybody can deviate and get his favorite alternative. So, a fortiori, just applying the same logic as the previous claim, we must be in a Nash equilibrium where everybody is already getting his favorite alternative, and therefore it must be optimal. And that's it. That's the proof for why this construction works. Now, of course, this is a game that no one would ever really want to play. It's really an existence theorem. It's not intended to be taken literally, but it's a useful existence theorem because it tells us basically what can be implemented and what can't. And once you know that something can be implemented, then you can worry about constructing games which actually make sense for people to play. And that's basically how the mechanism design literature has proceeded. We first see whether we can implement something at all, and then if we can, we try to construct a mechanism that is simple enough and natural enough so that we would actually want to use it. Now, sure. What happened to the microphone?
Thank you. In fact, I have 3 questions in the package. I hope that they're small enough. One question is that the construction uses infinite action spaces. Is it important? The second question is, can we have non-trivial mixed equilibria in this situation if we allow mixing strategies? And the third question is, can we extend this story to the version of Nash equilibria when no coalition, for example, of 2 agents wants to deviate? Thank you.
All very good questions. So the first question, you're correct that we have infinite strategy spaces here because players can announce any integer, and there's no upper bound. That actually is not important. What you could limit them to a finite number of integers, and instead of determining the winner according to the player that announced the highest integer, you could look at the you could use some modular rule. You could choose player I if the sum of the integers that the players are using equals I modulo the number of players. So an infinite strategy space is not necessary. Now, I haven't talked about mixed strategy equilibria here, and for good reason. This construction by itself doesn't rule out the possibility that there could be a non-optimal mixed strategy equilibrium. However, the argument can be generalized. I don't want to go into the details because they're even more complicated than this. But the argument can be generalized to rule out the existence of mixed strategy equilibria. Or actually, that's not quite right. There could be mixed strategy equilibria, but you could, if there were, they would be guaranteed to be optimal. And then the final question is, what if the concept is stronger than Nash equilibrium, and we want to make sure that if more than one player deviates at the same time, all of the equilibria of the mechanism are still optimal. So if I interpret your question right, you're not. I mean, one possibility would be to look at what's called strong Nash equilibrium. Strong Nash equilibrium says that you want something is an equilibrium when no coalition of any size can gain by deviating. But I think you were saying, what if you wanted Nash equilibria and strong Nash equilibria at the same time? Because you may not know in advance, as the mechanism designer, whether coalitions can form or not. They may be able to form, they may not be able to form. So you want the mechanism to be, you want the social choice rule to be implementable regardless of whether there are multiple player deviations or not. That's sometimes called double implementation, because it's Nash equilibrium and strong Nash equilibrium at the same time. Turns out that that's a little too demanding. If you have unrestricted preferences, so with unrestricted preferences, Pareto optimal correspondence can be implemented in Nash equilibrium, but it cannot be implemented in general with double implementation. However, there are some social choice rules that can be implemented with a rather limited restriction on preferences. For example, if there is some outcome that everybody agrees is Pareto dominated, that can be implemented. The social choice rule, which picks Pareto optimal, can be implemented in the way you suggest.
Thank you.
Marilee has a question. If you could pass the mic back.
Related to the same question, you mentioned the two extremes of Nash equilibrium and strong Nash equilibrium.
Yes.
But you could also, the question is if there is something in this literature that will define, let's define a K Nash equilibrium, or a K equilibrium will be an equilibrium that no coalition of size less than K could implement the social choice function.
That's right.
And it might be the case that maybe if K equals 2, that maybe you need more than 3, but maybe if more than 5 persons will play, you could implement such a thing. Are there results in this level? There are some limited results in that direction, but it's not a very well developed literature. So let me say first of all that here Betzalel Peleg did some work years ago on implementation in strong Nash equilibrium, and that was extended. Now I'm forgetting who did it. To something along the lines you're suggesting, where you're limiting. You're not allowing coalitions of every size. You're allowing only coalitions up to a certain limits. But what has not been done, to my knowledge, is the sort of double implementation exercise that I was talking about before, where you don't know in advance whether... See, strong equilibrium, in effect, requires coalitions to form if an improvement can be made. To implement something in strong equilibrium, remember, for implementation, it's not just necessary that you construct an optimal equilibrium. You have to make sure that there are no non-optimal equilibria. And strong equilibrium actually helps in the second part, because strong equilibrium is so powerful that it can kill lots of bad outcomes if you're sure that any coalition can form. But that's one problem with strong equilibrium, that you may not know that any coalition can form. And so the double implementation exercise, when, for example, coalitions up to a certain limit might form, but not beyond, that, to my knowledge, has not been done. That's still an open question. I think we are actually now officially out of time, and you're probably certainly out of energy. I've kept you going for 2 hours. I think we all deserve a break, and see you after lunch. And Elchanan, does everyone know where lunch is?
Yeah.